find the displacement, and internal member forces of the beam shown below. Show me that. You take a beam problem. Take a beam problem. So we take a continuous beam I will take a overhand beam. So A, B, C, D. Loaded with a uniformly distributed load on span AB and a central concentrated load on span BC and a concentrated load at the overhang. So we will take this span as 6 meters and flexural rigidity 2EI. Here it is 4 meters. So from this end it is 2 meters. That is central concentrated load EI. And same EI is for overhang. So this is the problem. So you have to find displacement and internal member forces. That's analysis. Analysis means we have to find the internal forces developed due to external loads as well as the displacements at various points. That's what I told. Analysis means that's what we have to determine. And of course, support reactions we have to determine. That is there. Support reactions as well as internal member forces, and that is static indeterminacy. And kinematic indeterminacy is the displacement at various joints, both static indeterminacy and kinematic indeterminacy. That's what we have to do. So first step, I told you analysis of any problem, plane problem can be done in 7 steps. I told already. The first step is that data, given data, you have to just prepare all the data. So our data, it is mainly data relates this unknown internal member forces or element forces, unknown internal element forces and unknown joint displacements. That's what we have to determine. The data for calculating the unknown internal element member forces. Element member forces means it is PM. Correct? As per our notation, PM is the vector of element forces. And unknown joint displacement, it is ds. Always displacements will be measured at joints. Loads also will be considered only acting at the joints or nodes and the corresponding displacement. Since loads will be in the global direction, displacements also has to be in the global direction. That's obvious. So that means in any problem, we have to identify what are ds, what are FPM to be determined during analysis. So in this problem also, we have to identify what are the member forces to be determined because of these external loads which are mainly acting on the members here. But now we have to find equivalent loads acting at the nodes or joints. Right? That is why we have to prepare a data first of all. Right? So since First we will take the load. Since all loads has to be acting at nodes or joints. Nodes of joints of the structure. We have to find equivalent joint loads. The equivalent joint loads is nothing but Pj minus Pms. Pj is the joint load. If there is a joint load already, we can take that as it is without any change. But if there is a member load, we have to assume each member to be fixed at the joints without allowing any displacements and find the fixed end actions. That fixed end actions you have to reverse itself. That's very, very important here. So first you assume if there is a member load, assume each member to be fixed at the ends and don't allow any displacement to occur at the ends and find the corresponding end actions. That we call it as PMF, equivalent end actions. How to find the end actions already you know at undergraduate level. So how to find the end actions because of various member loading and find that reactions or actions which are developed due to given load. And that thing you have to reverse. And if there is already a load existing at the joint, then you take it as it is. Interest problem, loads will be mainly on the joints, no member load. So there won't be any problem. But in beams and rigid plane frames, member load is there. That member load you have to convert it into equivalent joint load. So that means you assume each member to be fixed at the ends like this. Whatever member load is there, due to that member load, you have to find the member end actions. So you have like that. And of course, this is not a regular member, it is just a overhang. But we have to take that overhang portion also. So here you have 10 kilonewtons. This is for distance, you can take 2 meters. So here, applied moment is 10 into 2 at this point C. So resistive moment has to be 10 into 2, 20. It is 20 kilonewton per meter at C. Now here, this is 80 kilonewtons, this is 2 meters, this is 4 meters. So the end moments, it will be anti-clockwise here because applied movement is clockwise, suggesting will be anti-clockwise. Here it will be clockwise. Applied movement which is anti-clockwise, suggesting should be opposite to that. So in this value will be WL by 8. That you know, fixed end moment. That is 80 into 4 by 8. That is minus, of course, that is minus 40. And this will be plus 40 because we assume, take the sign convention for all the loads acting in any joints like this. All loads acting towards right, positive, all loads acting away from the joint, like this, away from the joints, upwards, this will take positive and clockwise movement about the z-axis we take as positive. So here, this is anti-clockwise, so it is minus 40, this is plus 40. And here, this is 50 kilonewton per meter. Of course, these are all kilonewton, meter, kilonewton, meter. So this span is 6 meters. So this will be WL square by 12. square by 12, it is 150. Minus 150 kilonewton meter, this will be plus 150 kilonewton meter. These are the fixed end actions we have. Therefore, now your PMS fixed end member actions will be, here it is minus 150, then here MAB is minus 150, MBA is plus 150, MBC is minus 40, MCB is plus 40, and this CD, of course, that you need not have to bother. It will be the overhand portion. It is anticlockwise. This is that. Only in the regular members, the member and actions, here it is minus 150, here it is plus 150, here it is minus 40, here it is plus 40, here of course it is 20. Any doubt? These are the fixed end actions, not allowing any displacement. Therefore, now you find kinematic indeterminacy where this joint displacement occurs. Here at A, it is fixed end, no displacement occurs. Here, now that I will mark it. So kinematic indeterminacy. So you have this beam like this. You have this beam. Here, what are the possible displacements are? Vertical displacement in global directions and a rotation. Here, both are not possible. Here, vertical displacement not possible, only rotation. I will call this as D1. Here, a joint C, vertical displacement 0, rotation, I will call it as D2. So, kinematic indeterminacy is 2. Is it clear? The possible displacement at joints of this plane same structure, that's continuous beam. At any joint, you have 2 possible displacement, vertical and rotation. Horizontal displacement, we assume it to be actually rigid, no horizontal displacement. So only possible displacements are these two. Out of that, depending upon boundary condition, these vertical displacements are not undergoing. Like that here, rotation is also not undergoing, only here. So your ds in this joint displacement, which is always corresponding to kinematic indeterminacy. So kinematic indeterminacy is 2, that is D1 and D2, and that is your unknown joint displacements which we have to determine during analysis. Analysis, we have to determine displacement at all the joints. So displacement at all the joints, at some joints displacements are 0. If you take out that and identify only those which are possible will happen, and that only is taken as ds, your unknown joint displacement. And the corresponding external loads corresponding to these kinematic indeterminacies, that is nothing but Ps. Correct? I told Ps is nothing but Pj minus Ps, PMS. So this corresponding Ps is equal to, that also you can work out here because this is the data. These are all known quantities, known from the data given. That's why I told you first step is very, very important. You have to do all this. Identify the nodes, identify the joints, mark all the nodal coordinates, and of course all those details you have to do in finite element analysis. In classical method, only this much is required, others we are not taking because we are not generating stiffness matrix using the general stiffness matrix as infinite element. Here we calculate and do it in classical method. So PS corresponding to D1 and D2. That is, D1 is nothing but this MBA moment as well as MBC moment. MBA plus MBC is the moment corresponding to producing this D1. This D1 is produced by these moments MBA and MBC. What is MBA, MBC? No external moment is given. Due to the loads, you have MBA, MBC. MBA, MBC are this plus 150 and minus 40. So it is 110. Sum MBA plus MBC is plus 110, but I have to reverse its sum. Right? I told Pj minus Pmf. The member and actions are assigned to be reversed. So this is minus 110. Is it clear? This is a very, very important step. Whenever there is a member load in all the mainframe problem, first you have to find the member and actions, then you have to reverse its sign and keep it as equivalent joint load. So that is for finding. Kinematic independency anyway you know, and the corresponding external loads which is known, that we have to work out. And next, corresponding to D2. Corresponding to D2, that is MCB and overhang MCD. MCB plus MCD is minus 40, plus 40 and minus 20. This is anti-clockwise. This is minus 20 and this is plus 40. It is 20. Plus 20. That's plus 20 sign and to reverse. So this has to be minus 20. So PS, DS I have generated. Where PS is known, DS to be determined. So these are corresponding to kinematic independency. So that is, this is your global coordinate. Global coordinate. These are all my global coordinates. Global displacements as well as global forces. Global displacements to be determined, global forces known. Because global coordinate is always horizontal, vertical, and rotation. Horizontal is not that here, only vertical and rotation. Unknowns are only this coordinate, 1 and 2. Corresponding to 1 and 2, the displacement to be determined, I am calling it as D1, D2, which is unknown. Corresponding to forces, the nodal forces is minus 110, and by this I told you how to find out because of member load. In stress problems, it's only joint load straight away, you can take that. And so next, local coordinates. We have to identify the member end forces. Which are the member end forces? So that by determining the stiffness matrix for a beam element, I told you only the independent end forces are the moments at the ends of the member. Though each member is subjected to a vertical shear at the ends, and the moments, the independent forces you can select either the moments at the two ends. So the moment you solve the moment at the two ends, the shear you can determine by equations of statics. By taking moment about this point, you can evaluate this reaction. By taking moment about this or by equating sigma B0, you can determine this. So this moment should be known. Or this force and moment at this end, or this and this, you can choose as the unknown. Here I told you, normally it is better to choose moments because transformation is not required because both these moments in local and global, they are same axis about the same axis. That's why they are selecting only the moments at the ends of the member as the unknown. So the local coordinates, we can mark it. These are the global coordinates. These are the local coordinates. The local coordinates to be determined are this. That we take clockwise always. This is PM1, PM2, PM3, PM4. These are the moments you have to determine at the ends of the member. The moment you determine the member and forces, so the analysis is over. Correct? Huh? So the unknown to be determined here, this is local coordinate. Local coordinate. So your local coordinate 1, 2, 3, 4. 4 coordinates locally, which we have to solve the internal member end forces. Only moments I will select, they are the independent. So PM will be equal to PM1, PM2, PM3, PM4 transpose. It's actually vector quantity and right in row with a transpose notation. This is 4 by 1 actually. So this is 2 by 1. Global unknown displacements, joint displacements are ds, unknown internal member forces are this. Correct? This much data you have to prepare. These are all only basic things. You need not waste this much time. Straight away simply write global coordinate, local coordinate with kinematic indeterminacy and their static indeterminacy. What is the internal forces to be determined? That's static. This is kinematic. That's what is first step. Right? You have to get the data by determining static and kinematic indeterminacies mainly. And of course, all loads to be taken care, they should act only as the joints. Accordingly, you have to select the global axis, local axis. Here, global and local axis, they are coincident because all members in beams, it is tight. That's why I told you beam problems are very easy when compared to truss. Right? Truss is an inclined member. Whenever inclined member comes, you have to find direction cosines. That's why the joint information, member information, we are determining in first step, data, beginning. So that next, second step. Second step, we have to find element stiffness matrix. Element stiffness matrix. After identifying what is that you have to do in the analysis, that is, what are the unknowns to be determined. That after identifying it, in second step you have to start proceeding your calculations. For that, first I have to determine the stiffness matrix in element coordinates, which already we know. So we know for any beam element, Km is given by 2EI by L into 2, 1, 1, 2. Choosing the end moments as the unknowns, right, as the independent forces to be determined. By choosing that, this is value. So now here in this problem, you have two members, one member, second member. I will call AB as the first member, BC as the second member. So KM1, first member, is equal to, I will apply this formula, 2EI by L. What is EI of that first member? It is 2EI. 2 into 2EI, it is 4EI divided by L is 6 meters into 2, 1, 1, 2. That is 2EI by 3, 1, 2, 1, 1, 2. That is Km1. It's very simple, straightforward process. Then Km2, member 2, it is again 2EI by L 2, 1, 1, 2. Second member, L is 4 meters. It is 2 into EI, 2 EI divided by 4, that is EI by 2. 2 EI by 4 is EI by 2, then 2, 1, 1, 2. Therefore, the element stiffness matrix of the entire structure Km. So you have to assemble Km1, Km2, Km3 diagonally, I told. In stress problem also, here also. In stress it is only one element, AE by L. Here it is 2 by 2. Right? You have to take, because 2 N elements. There it is only one axial force, either tension or compression. So here it is EI by 2 here, 2 EI by 3. The LCM is 2, 3, 6. I will take EI by 6 outside for all the elements. So if I take EI by 6, here this is 2 by 3, 1 by 6. So EI by 6 I have taken outside. So this will be 4 into 2, 8. Then 4 into 1, 4. This will be 4, this will be 8. Correct? Huh? Because 8 EI by 6 is 4 EI by 3. That's the first element. 8 EI by 6 is 4 EI by 3. So if you multiply this, you will get 4 EI by 3. Next, this will be 2 EI by 3. 1 into 2 EI by 3. So here I have taken EI by 6 outside. So it is 2, 2, 4. That's why this is 4. 4 into EI by 6 is 2 EI by 3. Next, again, this 4 into EI by 6 is nothing but 2 EI by 3. 2 EI by 3 into 1 is 2 EI by 3. Like that. Only for convenience purpose. Here, 0, 0, 0, 0. Here also, it is 0, 0, 0, 0. First element. This is first element. Then you have one more. Second element. I have to write diagonal. Another element. Second element. This is the stiffness. EI by 6 I have taken outside. Here you have a EI by 2. So these elements have to multiply by 3. So 3 into 2, 6. 3 into 3, 3, 6. So this is my element stiffness matrix of the entire structure. This is second step. This was the same thing. Next, you have to find rotation or transformation matrix, or you have to get it. Then we can use the relationship PS equals KS ds. That KS we have to generate next step after finding the transformation matrix. So that is the third step. Third step is transformation matrix. Transformation matrix. That is R. I have to find R. So I told you how to find R. We have to apply unit load or unit displacement, not load, unit displacement along each of the global coordinates, one at a time. That is d1 equals 1 I have to apply, d2 equals 1 I have to apply, keeping all of the displacement fixed, not allowing, and find the corresponding global local displacements. So that means this is another important step you have to remember and do it correctly. And of course this overhang is there, that you don't have to bother. Overhang is not a regular member. So I have to apply a unit displacement along one first, keeping all other displacements not occurring. So there are two global coordinates. I have to apply unit load along each of those global coordinates one at a time. So here if I apply a displacement in the clockwise direction, because that's what I have taken here, d1 like that, this will go up, this will come down. So it will, this I should not move. It has to be like that. So this is fixed. Here also it is fixed like this now. In the rotation, like this I have rotated like that. I have given rotation. So that means, that is, if I draw a tangent, so this is that rotation, unit rotation I have to give. Correct? This is very simple. At any joint of continuous length, this is what we have to do. So then find the corresponding displacements in the local coordinate. So what is in this local coordinate? There are 4 local coordinates, right? I have applied unit load along one global coordinate. I have to find corresponding local coordinate displacement. Here, corresponding to this, there is no displacement because we are assuming the joint to be fixed. Then corresponding to 2, it is 1. Corresponding to 3, it is 1. Corresponding to 4, again it is 0. So it is very, very simple. So therefore, the elements of the first column of that rotation transformation matrix is 0 corresponding to PM1, corresponding to PM2 it is 1, PM3 it is 1, PM4 it is 0. I have evaluated the first column. Next, I have to apply unit displacement corresponding to global coordinate 2. This global local I am using quite frequently, that you should know now. What is global coordinate? That is 2 coordinates. Local coordinate 4. So that clearly it should be there in the mind. So here I have to apply now along global direction. D2 equals 1. So again, all the others we have to restrain. So here, no displacement because it is restrained. PM1 is 0, PM2 0, PM3 also 0. This it will move like that. So that means it is like this now. It is fixed like that, assume. So here I have applied it. Here displacement is 1. Right? In truss problem, you have to take the component correctly, that's all. They are also same principle. You have to give horizontal displacement, vertical. There is no movement coming. Here movement is coming and it is easy also. That's why I told you, beam problems are more easier. So here, the displacements corresponding to local coordinates, when you give unit displacement along this global direction, it is 0, 0, 0, 1. Therefore, your all matrix will be combination of this 0, 1, 1, 0, 0, 1. So it is a 4x2 matrix. I told you Rij, the forces developed along local directions when unit displacement is given along global direction. Rij, I told you define Rij is the displacement corresponding to member coordinates. There are 4 member coordinates. When unit displacement is given along single coordinates. That is 2 coordinates. So this is a very important. Next step, 4th step, find global stiffness. For determining this global stiffness matrix, I have done this much exercise. It is only corresponding to only kinematic severity. That is the shortcut procedure in classical method of analysis. In finite element, we are determining for all the coordinates, generalized coordinates, and take finally the reduced one on which displacements are possible. That's the advantage. There we are using computers, so time as well as the time is not at all a problem, and difficulty is also not there. Computer will do it. So there only we will see Km for all the members. We will work out potential transfer matrix for all. Then finally take only global stiffness matrix for that. So that is the only change. Otherwise, basic concept wise, both is classical method and finite element. There is no difference at all. Finite element is lengthy, that's all. That's the only thing. Then lengthy question doesn't arise at all because we are using computer. That's all the thing. So here, global stiffness matrix, just now I told principle of contragradients. So global stiffness matrix is given by RT into Km into R. That is relationship. So R is known, Km is also given for the entire structure, find for the entire structure for the stiffness. Then use the relationship between force displacement relationship PS equals Ks here, solve ds and temperature. That's all the simple 7 steps. Nothing other than that. In any big problem, any loading, like classical method as well as finite process. So, and take this, therefore Ks is equal to, I will evaluate this RT Km R. So this RT is nothing but 0, 1, 1, 0, 0, 0, 1. I could write the transpose of this. Change goes to column to rows. Into Km is nothing but year by 6 into that 8, 4, 4, 8, 0, 0, 0, 0, 0, 0, then 0, 0, 6, 3, 3, 6, multiplied by R, that is 0, 1, 1, 0, 0, 0, 0. So if you perform this complete matrix operations, you will get Ks. I will have got a calculation we have done to give you. Ks is given by, because this is 2 by 4 matrix, this is 4 by 4, this is 4 by 2 matrix. First, if you multiply this column equals row, resulting will be 4 by 2 matrix. That 4 by 2, this is 2 by 4. 4 will go 2 by 2. So this Ks will be a 2 by 2 matrix, and that is given by year by 6. That year by 6 I have kept outside 14, 3, 3, 6. 14, 3 and 3, 6. This is what I kept. It's only matrix operations. This also you can feed straight away and get the results. Next, 4th step. Now 5th step. 5th step. Fifth step, formation of equations, or it is called force displacement relationship. That is the equation P is equal to K. So that is, I will formulate the equation which Px is equal to Ks ds. This is the equation. Px, already you know, we have generated in the very first step. Px is minus 110 and minus 20. that is corresponding to external load. So that is minus 110 and minus 20 Ks we have generated here by 6 into 4336 and ds is d1 d2. That's the unknown. Now you have two equations. One equation, second equation you can solve for d1, d2, or you can invert this Ks matrix, multiply by this ds, you will get ds. Either inversion or simultaneous equation solution. Either one you can do it. So let's solve it on 6 steps to find unknown displacements. Unknown displacements. That is ds. That's what our aim. In the first step itself I told you have to find the joint displacements ds. That's what we have identified. So that is known here ds. So solving the above equations either by inversion or by solution, you will get d1 d2 is equal to this d1 d2, you will get 1 by ei minus 48 and 4. So that means d1 is minus 48 by ei, d2 is 4 by ei. That's all. d1 d2. That means this is between unknown joint displacement. Our second aim of problem. And finding the unknown displacement. Then inter-member forces we have to get to. That is our last step to find the internal member forces. These are the 7 steps I have indicated. Even for the stress problem also I did the same thing. Last step. So I will give you the formula that PM is the internal member forces correspond to local coordinates. All my PM1, PM2, PM3, PM4. PM1, PM2, PM3, PM4. Then once I determine the member and moments, shears also can be determined by status. Everything is known, that's all. Clear? That's how we do it. So PM is given by here there was a member load. That's why that member load also we have to take that fixed length actions. PMS. This is the extra time coming. PMS plus Km into dm. This is PM equals Km dm. So instead of Km dm, I have to add this also, PMS also. That is corresponding member fixed length action. That's all the change. Nothing other than that. Of course, dm is nothing but or ds. Correct? R is known, ds is known, this is the ds. R is known, ds is known, km is known, that also you have determined. So you multiply that 3 matrices. And IPM also I have determined in the very first step, PMF. Fixed member reductions corresponding to this. If you add, you will get PM. This is about determining unknown internal member forces. Thereby, we have evaluated what is the thing we have to do in analysis of the problem. So if you do that, of course, I will leave that step completely. This PM is nothing but all the forces, PM1, PM2, PM3, PM4, that is equal to PMS, I have left it out, it is minus 150 plus 150 minus 40 and it is plus 40 and of course overhang if I take PM as PM5, that overhang moment is known. PM5 is minus 20. That is known already. This, otherwise this PM5 you can leave it if you want overhang. I don't consider. The PMF plus this Km is nothing but divided by 6, 8, 4, 4, 8, 0, 0, 0, 0, 6, 3, 3, 6. You see that Km multiplied by dm is all ds. All is, again, all is 0, 1, 1, 0. This is 3 zeros, 1 into dx is 1 by ei into minus 48 and 4. This multiplication you have to do, because this is 4 by 4 matrix. This is 4 by 2. This is 2 by 1. So if you multiply 4 by 2, 2 by 1, this column will get cancelled, you will get 4 by 1. This is 4 by 4. 4 by 4 by 4 by 1, again 4 cancels, you will get 4 by 1. This is 4 by 1, this is also 4 by 1, this is also 4 by 1. This 4 by 1, 4 by 1, you add the two matrices, you will get unknown thing. Final result, I will give you so you can verify final end moments. PM is given by minus 182, 86, minus 86 and 20. This is, plus 20 and overhang minus 20. There also it is satisfied. So it's a perfect thing. So this is about analysis of continuous beam problem. I have explained thoroughly all the 7 steps involved, and I have given how to take whenever member load is there, how to work out the problem. The rest and all, it is similar to rest problem. Next, we will take one more example wherein supplemental support, if it is included. That I will take up one more example. Take second example, another continuous beam problem, because syllabus says